Assalamualaikum. Good afternoon, guys. Okay. This recording is being made since we have internet problem just now. Or not we. Us here in UMP. Okay, in block A1, we have server problem. So all of us cannot connect with the internet. Okay. Thus, okay. I'm going to do recording for this chapter 9 and 10. Okay, so we stopped at the indicators for EDTA titration just now using the Microsoft Teams channel. Okay, so for this recording, we are going to start straight away at the indicators. Okay, so as I said just now, there are three organic dye that is used as the metal ion indicators. If you want to determine the copper, you can use fast sulfone black. Okay, so the color changes is from purple to green. Okay, and then if you want to determine calcium and magnesium, you can use erythrom black tea. Okay, and the color will be changed from red to blue. Okay, and the last one, calmagite. It is also for calcium and magnesium. Okay, the color change from wine red or sometimes purple. There is a difference here. Okay, sometimes you see as red, sometimes you see it as purple, and it will turn into blue. Next, okay, a typical titration used in the lab is the reaction of magnesium 2 plus ion with EDTA at pH 10 with calmagite indicator. What happened is that the magnesium with the indicator, okay, it combined with the indicator, it will be red color, and then react with the EDTA, it will form the magnesium EDTA. Okay, so this magnesium EDTA is colorless, but the one that change the color is the indicator. When it reacts with magnesium, it is in red color. But then when the magnesium react with EDTA, now the indicator will be alone. It will turn into blue. So this indicator is the calmagite. Right, and then this is the steps. Okay, what happened during the titration? Okay, as usual, when we are talking about titration, we will have titration curve. Now, we are looking at the EDTA titration curve. Okay, the titration reaction is between the metal ion. Okay, depends if it is magnesium, this M will be Mg. If we are titrating the calcium ion, this M will be Ca. Okay, react with EDTA and it will become metal with EDTA. Okay, so the titration curve is a graph of PM. Okay, remember acid-base titration pH. Precipitation titration is PCl. For EDTA titration, it is PM. This capital M refers to the metal. It will change depending on what metal is reacted with the EDTA. If calcium, this one will be PCA. If magnesium, it will become PMG. If copper, it will become PCU. And this PM, we know that the small p refers to negative log. And the capital M here is the concentration of the metal ions. If calcium, so this concentration will be concentration of calcium ions. Okay, so negative log the concentration of metal ions versus the volume. Again, volume, and depends what is the titrant that you use. In this case, for complex geometric titration, it is EDTA. So at the x-axis, you have volume of EDTA versus the negative log of concentration of the metal ions. Okay, as I said, they are similar. Okay, so just now I said that when you have a specific metal ions, for example here you have calcium ion, okay, this PM will be PCA. Okay, so negative log the concentration of calcium ions. Okay, it is at the different pH. Okay, and you can see that the curve also different based on the pH. Right. Titration methods employing EDTA. Okay, similar to precipitation titration. There are few titration methods employing the EDTA. Okay, it's either the direct method. Okay, direct method. You can directly titrate the titrant and titrant. There are also potentiometric methods where you use the electrode. And we also have spectrophotometric methods. Okay, it is a measurement of UV absorption. Okay, after you do the titration, you put them in the UVs. Okay, for direct method, it is the changes of color of the indicator. And then we have another two titration method for EDTA. We have back titration. Okay, remember for precipitation titration, we have vol height, which is back titration. So in EDTA titration or complexometric titration, we also have back titration. And the method is the same. But the one that is different, what you use as the agent. Okay, in precipitation titration, what you use for the precipitating agent. In complexometric titration, what you use as the complexing agent. Okay. And the last one is displacement method. You displace the ion that you want. Okay. And this is the calculation involved for complexometric titration. Okay. Example, you are given 50 ml unknown sample solution. Analyze for hardness using complexometric titration. What does it mean by hardness? Some of you might be familiar with the words water hardness. Water hardness, we determine the content of calcium in water. Kalau you biasa mandi, rambut you jadi keras. Dalam air tu maksudnya tinggi dengan calcium carbonate. That will cause the hardness of the water. Ataupun kadang-kadang kita boleh nampak daripada dalam air tu ada, kalau you biarkan air tu lama-lama dalam cawan, you boleh nampak white precipitation. That one is calcium carbonate. Okay, and it cause the water hardness kalau kena rambut you keras. Itulah. Okay, so this water hardness is determined by the jabatan air. Jabatan air biasanya akan look at the content of calcium in the water to determine the hardness. Kalau banyak sangat, kena complain lah. Okay. Dia ada dia punya limit dia, berapa calcium carbonate in the water should be. Okay. Because it will cause other problems. Okay. Clotting lah. Macam-macam lah. Okay. So, to determine the water hardness, the content of calcium carbonate in the water, we can use complexometric titration. Okay, so we have 50 ml unknown sample. Okay, and then we require 25.55 ml of 0.01 molar EDTA solution for complete reaction. Okay, maksudnya complete lah, and dah capai endpoint. So this question asks you to calculate the hardness of the sample in molarity. Means that the concentration of calcium ions. Kalau dikata calculate hardness. Okay. In molarity maksudnya dalam bentuk concentration. Ada juga kita minta you calculate hardness of the sample in gram. Maksudnya mass of the calcium ion. Okay. So you are given the chemical formula, okay, chemical reaction, and we know that when we are talking about water hardness, it involves calcium ion. So this calcium ion will react with the EDTA, okay, EDTA in 4 minus in the form of ion, okay, and you will get the calcium EDTA 2 minus. So you are given the volume of the unknown, which is 50 ml, while you need only 25.55 ml, 0.015 molar EDTA to completely react with the 50 ml calcium. So determine the molarity. Okay. So first what you need to do, okay, similar to previous chapters, okay, for precipitation titration, the first one we need to calculate the number of mole. In this case, the information given is for EDTA. So we can calculate the number of mole for EDTA. Okay, and after we get the number of mole for EDTA, we can now calculate the number of mole for calcium ion based on the chemical formula given. In this chemical formula, we know that 1 mole of calcium react with 1 mole of EDTA. So the number of mole will be the same. And from this number of mole, we can calculate the molarity. Since we know the volume of the calcium ion, 50 ml, so we can straight away divide the number of mole with the volume of calcium ion. Then we get the molarity of calcium ion. Okay, so we call this as the hardness in molarity. But usually hardness we will calculate in gram. Okay, lagi nampak lah kalau kita cakap dalam bentuk molarity kita tak nampak, tapi dalam bentuk mass kita boleh bayangkan banyak mana kalsium yang ada dalam air. Okay. But they are similar, depends on the question. If the question asks you to give in molarity, so molarity lah. And then, as I said just now, sometimes usually we report the hardness. Kalau jabatan air tu dia report dalam bentuk milligram of calcium carbonate per liter. Okay, so we have number of mole. Just now we can use this number of mole to calculate the mass of CaCO3 by multiply with the molecular weight of CaCO3, 100.09. Okay, so we get the mass. From this mass, we know that there is 0.0384 gram of calcium carbonate in 0.05 liter or 50 ml of water sample. Kalau 50 ml sikit kan? Kita ada 0.0384 gram. Kalau kita ada 1 liter, berapa? Okay, so we divide by the volume, we can see that we have 767 milligram in 1 liter of water. Okay, so banyak mana, boleh bayangkanlah 700 milligram. Okay, kalau you ada 1 gallon air, you boleh nampak lah white precipitate of calcium carbonate. Okay, so this is the hardness. Okay, we use complexometric titration to determine the water hardness. Alright, so that is for complexometric titration. Okay, and we can also use the same methods for precipitation titration to come up with the titration curve. Okay, kita boleh tanya juga. So we can ask you to find the PCA at before the endpoint, and then at the endpoint after that in excess. Okay, so boleh come out cara kira dia sama dengan precipitation titration. Okay. So next we move on to the last chapter, which is chapter 10, redox titration. Okay, so for redox titration, what you need to know is the oxidation and reduction reaction. And you can imagine that now we are using the electrode, okay, to determine the potential cell, potential cell of our redox titration reaction, okay. So what happened in redox titration, okay, we know that Re refers to reduction, okay, and OX refers to Red reduction, OX refers to oxidation. Okay, there will be oxidation and reduction reaction happen to in the redox titration. Okay, for example, here we have the reaction between cesium, cesium 4 plus with iron 2 plus. Okay, and there is redox reaction happen. One of them will undergo oxidation, one of them will undergo the reduction reaction, and from cesium 4 plus it becomes cesium 3 plus. From iron 2 plus it becomes iron 3 plus. Okay. So what does it mean by oxidation and reduction reaction? Okay. For oxidation, oxidation is when the element lost the electron. Okay, lost electron. Oxidation, lost electron. So when we lost electron, bila kita hilang negatif, dia akan jadi positif or more positif. Okay. Reduction is when the element gain electron. Okay, dia akan jadi lebih negatif. Okay, so here, when you see cesium from 4 plus become 3 plus, now the positivity reduce. When the positivity reduce, it means that it gain electron. Okay, when it gain in 1 electron from 4 plus minus plus electron, 1 electron. Okay, bila plus electron ni maksudnya dia jadi lebih negatif lah. So it become the positivity reduce. So we can say that this cesium has gained 1 electron. Okay, gaining 1 electron is reduction reaction. Iron 2 plus become more positive. More positive mean it lose electron. Okay, so losing electron, this iron undergoes the oxidation reaction. Okay, so in oxidation, we use reducing agent. Okay, reducing agent. Jangan tertukar pula. Kalau oxidation reaction, agent yang kita guna adalah reducing agent because it will help the element to lose electron, to reduce the electron. To reduce the electron. For reduction, we use oxidizing agent. This agent will help in gaining the electron. Okay, so jangan tertukar lah. This oxidizing agent, or sometimes we call it as oxidant, involved in the reduction reaction. Okay, it gain 1 electron. Tambah 1 electron, gain lah. For reducing agent involved in oxidation, it lose 1 electron, or sometimes we call it as reductant. Okay, so please remember this concept. Okay, concept of oxidation and reduction reaction, and concept of reducing and oxidizing agent. Okay. Why? Because you are going to come up with the balance reaction, balance equation. So the difference between this redox titration with other titration, if you want to balance the equation, the chemical equation, it is not as simple as before. When you are dealing with redox titration, redox reaction, what you need to do to get a balanced equation is by looking at the half reaction method. Okay, so these are the things that you need to consider when you want to come up with a half reaction method. Okay, yang ni you dah belajar dah sebenarnya dalam matrik, dekat matrik dah belajar, dekat STPM pun dah belajar. Okay, so you can go through again what you need to consider when you want to come up with a half reaction method. Once you come up with a half reaction method, you will get the balance equation. So let's see one example. Okay, you are given the exercise, but today I'm going to show you. Exercise usually students need to do by your own, okay? Because we already give you the answer. But today I'm going to show you the first example on how to balance the redox equation. You are given this equation, but this one is not balanced yet. Okay, kalau you tengok nombor dia tu tak balance lagi. Okay, in this case you cannot simply Mn2 plus, so we can write 2 here. No. Okay, you need to consider the half reaction. What does it mean by half reaction? You need to come up with which one of the element here undergo reduction and which one undergo oxidation. Okay. In this case, I know that you guys tak boleh nak hafal banyak benda kan? So for half reaction, the standard potential for half reaction will be given. Okay, so the example. Okay. So this is the standard potential will be given in the appendix. Kalau kita minta you buat lah, kita akan bagi. Okay, this one is given. So as you can see here, the title, standard reduction potential of half cell. Okay, so in this appendix or in this document, you are given only on the reduction. So if the element undergoes oxidation, you kena terbalikkan dia lah. For example, chloride. Okay, chlorine. For reduction, chlorine gain 2 electron, become chloride ion. If in the reaction given, the chloride ion oxidize into chlorine, so yang ni reaction equation ni akan terbalik lah. 2 chlorine will produce 2 chloride ion will produce 1 chlorine plus 2 electron. Okay, saya tunjuklah kat sini. Tak apa, nanti kita tengok contoh. Okay. So, based on the list given, okay, you need to find the half reaction for MnO4 minus. Okay, make sure in the half reaction, in the standard reduction potential, okay. So in this list, you need to find the MnO4 minus that will produce, look back to the exercise given, find MnO4 minus that produce Mn2 plus in the list given. Okay, cari. Because we also have Mn2, MnO2, we have others, and you need to find the which one that give the same reaction that we want, that the question asks. Okay, so the third one, MnO4 minus will produce Mn2 plus. So this one that we want in our question. Okay, ambil yang tu. First, we need to know whether it is reduction or oxidation. So MnO4 minus produce Mn2 plus in the standard reduction potential given MnO4 minus plus 5 electron. So it gain electron. So when it gain electron, it is reduction. Okay, is MnO4 minus undergoes the reduction reaction. Saya pun tak hafal, you tengok juga dekat dalam list tu yang kita akan bagi dalam appendix. Okay, so the MnO4 minus plus 8H plus 5 electron produce, saya tulis kat bawah ya, sebab saya nak tulis untuk oxidation pula dekat sebelah sana. Tapi dalam you punya assessment, you kena tulis ni lah, betul-betul lah. Mn2 plus 4H2O. Okay, so this is half reaction for MnO4 minus. Okay, and since it is plus 5 electron, it gain electron. So we know that it undergoes the reduction reaction. Okay, and then look at find the reaction of NO2 minus that produce NO3 minus. Okay, NO2 or NO3, kita cari. Okay, here. Kalau you dah biasa guna, senanglah nak nampak. NO3 minus plus 2H plus 1 electron, it produce NO2 and H2O. Okay, remember, this one is standard reduction potential. It is given for reduction reaction only. Since in our question, we start with NO2 minus. Okay, NO2 minus. So it is undergoes oxidation, means that it lose electron. Okay, so from the standard reduction potential given, it is given in reduction. So we need to change from NO3. We need to change. It will become NO2 minus plus H2O. Sebelum ni dia jadi produk kan. Bila kita dah tukar dia jadi kepada oxidation reaction, dia akan jadi reactant. Okay, forming the NO3 2H plus 2 electron. Okay, as you can see here, this NO2 minus lost 2 electron. Bila dah masuk dekat produk, maksudnya dia hilang 2 electron lah. Okay, when it lost electron, it will be under oxidation reaction. Okay, so this equation is not balanced yet. Okay, so how to balance the equation is by looking at the number of electron. In reduction, we have 5 electron, while in oxidation, we have 2 electron. So to balance this equation, for reduction reaction, we need to times 2. And then for oxidation reaction, we need 2 times 5. Okay, so that both of them will have 10 electron. Okay, after we have we have times 2 here, we should get 2 MnO4 minus plus 16H plus 10 electron, giving 2 Mn2 plus 8 H2O. Okay, this is for reduction. And then for oxidation, times 5, we will have 5 NO2 minus plus 5 H2O. Okay, producing 5 NO3 minus plus 10 H plus 10 electron. Okay, so now both of them already have the same number of electron. What we need to do is to cancel out those that those in reaction in reactant and those in product. So I'm going to change the color of the pen. Okay. Alright, look at the equation. First, in the reduction, we have MnO4 minus. Is there any MnO4 in oxidation? No, so we cannot cancel this MnO4 minus. Next, we look at the H plus. Is there any H plus in the oxidation? Yes, but make sure they are this one in as a reactant and this one as a product. Baru boleh cancel out. Kalau both in reactant, we need to add them out. Kena tambah. Kalau dua-dua dalam reactant, kita kena tambah. Kalau dua-dua dalam produk, kita kena tambah. Tapi kalau salah satu dalam as a reactant, another one is a product, we need to cancel them out. Okay, so we have 16H plus in the reduction as a reactant. And we have 10 H plus as a product in the oxidation. We can cancel them. But we still have remaining 6 H plus here. 16 tolak 10 ada 6 lagi lah dekat reduction. Okay, dekat bahagian MnO4. And then look at the number of electron. Both have 10, so we can cancel them. Next, we look at the product for reduction. We have Mn2 plus. Is there any Mn2 plus? No. So we leave it. And then the last one we have H2O. Okay, we have 8 H2O for reduction and 5 H2O for oxidation. They are in different part. Okay, so kita kena cancel lah. Kalau dua-dua dalam reactant, dua-dua dekat sebelah kiri, kita kena tambah. Ataupun dua-dua sebelah kanan, kita kena tambah. Tapi sekarang dia dekat satu sebelah kanan, satu sebelah kiri, kita kena cancel. So since we have only 5 in oxidation, but 8 in reduction, we will have remaining 3 H2O. Okay, to balance this, after we have cancelled out the same component or same element, we now can come up with a balanced redox equation. Okay, just ambil je apa yang dekat sebelah kiri untuk reduction dengan oxidation, masukkan. So we have 2 MnO4. Okay, 2 MnO4 minus, okay, apa lagi kita ada? 6H plus. And then in oxidation we have 5 NO2 minus. Okay, 6H plus. From reduction we have these two elements, two compounds. And then in oxidation we have one compound. Okay, and then look at those in on the right hand side as a product. For reduction, we have 2Mn2 plus, and for oxidation, we have 5NO3 minus, and also 3H2O. Okay, 3H2O from reduction. Okay, so now we already have the balance equation. It is not similar with previous one that we have done. For reduct titration, first you need to come up with a half reaction. Look at the standard reduction potential given, the list in appendix. You are given in reduction, so for those undergoes oxidation, kena terbalik. Yang kiri ke kanan, yang kanan ke kiri. Okay, and then after that balance the, make sure the number of electron for both of them are the same. Okay, kalau kat sini darab 2, kat sini darab 5. Okay, in this case lah. Banyak lagi equation lain yang kita boleh bagi. Okay, after the number of electron already the same, now look at the same component, whether they are both of them in the at the right or at the left. We need to total them up. If they are at different place, one in the left and one in the right, you need to cancel them. Okay. And last one, you will get the balanced redox equation. So don't worry, this standard potential will be given. Okay. So in this case, you are given the reduction again. So gain electron is reduction. If the compound undergoes oxidation, ini akan dia terbalik lah. Ini arrow bukan sama dengan ni. Ini arrow. Okay. So dia akan dia terbalik. Right. In redox titration, you also need to calculate the standard cell potential, E naught cell. Okay, so this potential, the standard cell potential is different between the standard of half cell potential. In the list given here is the half standard potential. Okay, and it is different from the standard cell potential. E naught cell, kalau kita tulis cell kat sini, dia untuk standard cell potential lah. Okay, if you are given E naught cathode and E naught anode, it is for half reaction that you can get from the list given. Sometimes we also write down as E naught reduction plus negative E naught oxidation. Okay, why there is a negative here? Because in this list, you are given for reduction. Okay. Once you change them into oxidation, okay, macam tadi terbalik kan, daripada reduction jadi oxidation, dia terbalik equation. The chemical equation also will be changed from right to left and left to right. This E naught will be negative E naught. Sini positif kan. Okay, so kita bila kita balikkan dia akan jadi negative E naught. That's why for standard cell potential there is a negative here. Okay, so let's look at the example given. You need to calculate the cell potential for the oxidation of zinc by silver ion. Okay, so this you are already given the balance equation. Kalau you nampak ada nombor je kat depan ni, maksudnya dah balance lah. Okay, so how to know whether there are reduction or oxidation? Okay, as you can see here, this silver ion become Ag, solid, become solid silver, which means that it gain electron. Daripada positif dia jadi kosong. Maksudnya dia gain electron. So gaining electron means that it undergoes the reduction reaction. Okay, gain one electron, become the solid silver. Okay, so it undergoes reduction. You can straight away use the information given in the list. Ag plus 1 electron produce Ag solid. And you can straight away take the value of the E naught given in the list. Yang list yang kita akan bagi ni, kalau untuk Ag tadi, ada tak kat sini? Tak ada, dia ada kat sini. For silver, yang ni baru sikit lah, kita bagi contoh sahaja. Kalau untuk appendix kita bagi yang penuh ni lah. Okay, Ag, let's look at for Ag. Okay, this one here. So it is undergoes reduction. Gain electron undergoes reduction. So the value for E naught half reaction here is 0.80, positive 0.80. So you can straight away take this value because it's already in reduction. And then for another element is zinc. So zinc, this one here 0 become 2 plus. Daripada kosong dia makin positif. Makin positif maksudnya dia hilang elektron, lose electron. So zinc, okay, how to come up with this? Kalau you tak ingat, maksudnya kena tengok dekat standard reduction potential lah untuk zinc. Okay, of course when it is reduction, dia akan terbalik lah. Okay, find the zinc. Okay. So this one is for reduction of zinc ion. Zinc 2 plus 2 electron become zinc solid. So this one is reduction. In this question, zinc now undergoes oxidation. So dia akan terbaliklah, zinc solid produce zinc 2 plus 2 electron. Okay, so as I said, since we change the direction, this E naught, okay, in the standard reduction potential, the value is negative 0.76. Negative 0.76. Okay. So since we change the direction now, we need to put negative in front of the E naught half reaction. So here, to calculate the E naught cell, okay, you boleh ambil salah satu lah. Biasanya saya akan ambil yang ni. You boleh juga, saya akan ambil yang ni. You boleh juga guna untuk yang cathode dengan anode. Tapi saya untuk mudah ingat, saya guna yang ni. Mana satu reduction, mana satu oxidation. Okay, so put them in this equation. So negative E naught equal to 0.76. Jadi positif lah, negatif jadi positif. So dia akan jadi positif. Tambah 0.76. Okay, so you get the E naught cell equal to 0.8 plus 0.76. Okay, why it becomes positive here? Because we change the direction from the reduction to oxidation. Yang value yang ni dalam kurungan ni daripada reduction potential list. Since we change the direction, we need to put negative in front. That's why dia jadi positif kat sini. Okay. Alright. So other than the cell potential, okay, we also can calculate the free energy by using this equation. Okay. The free energy is equal to negative number of electron, number of mole of electron. Okay, 2 mole, 2 electron, so the N will be equal to 2. F is Faraday constant, so this one is given. Ataupun memang constant lah, dia memang kita ambil je value ni, masukkan dalam equation. And then E cell, after you calculate using the equation, the previous equation, then you can get the free energy change. Okay. Ini you dah belajar dalam physical chem kan. And the last equation, last calculation involved in redox titration is the Nernst equation. Nernst equation, yang kat sini kalau you tengok, Nernst equation E cell, we calculate the potential for cell, not the standard potential. Standard potential ada note kat atas ni. E not cell is the standard potential. We calculate before, yang you kena cari half reaction dulu, lepas tu berapa potential untuk half reaction, baru you dapat E not cell. This E cell, tanpa note kat atas ni, it is refers to the Nernst equation. Okay, so the E cell is equal to E not cell, the standard electric potential, minus RT. R is the ideal gas constant. Okay, constant memang ni lah nilai dia. T is the temperature in Kelvin. Okay, divide by number of mole of electron times Faraday constant ln Q. So this Q is product over reactant. Okay, product over reactant from the chemical equation. Okay. So simplify after kita dah masukkan semua ni, kita dah ada constant kat sini, kita masukkan itulah terus. Okay, so kita simplify, dia akan jadi at last E cell is equal to E not cell minus 0.0592 over N, number of mole of electron, times log Q at 25 degree Celsius ataupun boleh tukar kepada Kelvin. Okay, kita akan dapat ni lah. Ini kita dah masukkan 8.314, temperature 25 degree Celsius, tukar kepada Kelvin, and then Faraday constant kita dah masukkan, kita tukar daripada ln kepada log, okay, 2.303. So kita dapat value yang ni. So ini dah simplified, so usually we are going to use this one straight away. Okay, we assume that the reaction occurs at 25 degree Celsius. Okay. So let's look at the example for Nernst equation. Oh, tak ada example, exercise terus. Okay, for exercise, so I'm going to show you how to calculate to solve this exercise. Important things that you need to pay attention here is the pH value. Okay, why? We are going to look at why after this. Okay, so you are given a solution of 10 to the power of negative 3 molar, okay, in Cr2O72 minus, and 10 to the power of negative 2 molar in Cr3 plus. Okay, if the pH is 2, what is the potential of the half reaction? Remember, different pH, you akan dapat different different curve, different titration curve. Okay, that's why you need to pay attention for this one. And you are going to use this one later in the calculation. Okay, so the question asks you to find the potential, which is E cell. Okay, first, you need to find the half reaction. Okay, for each of these. You already given the balance equation here. Oh, ni tak perlu cari half reaction dah. Kita straight away guna the E cell. Equation. E cell equal to E naught cell, E naught minus 0.059 over N log Q. Okay, macam mana nak tahu? Sebab dia dah bagi concentration. Bagi concentration here. So we are going to use this log Q because log Q is the concentration of product over concentration of reactant. Okay, so since the concentration is given, So we consider to use this equation. Okay, so E cell equal to E naught cell, okay, minus 0.059 over N log Q. So what is the E cell here? Kita kena cari juga sebenarnya half reaction, tapi kita tak perlu come out dengan tak perlu tunjuk lah. Kita terus cari dia punya standard potential for half reaction. Okay. Cr2O7 2 minus give you Cr3 plus. Okay. Get the list given Cr2O7 2 minus ini. So kalau tengok kat sini dia reduction lah. Okay. So it is 1.33. So it is 1.33. Okay. Minus 0.059, divide by number of mole of electron. So number of mole of electron here is 6. So divide by 6. Log concentration of product. So product here is Cr3 plus. We consider only ion. So Cr3 plus is 10 to the power of negative 2. Ini from the question given. But look at the number of mole in front. So that one will be to the power of 2. Divide by reactant dia Cr2O7 2 minus. And H plus. Okay, kita ambil yang ion. Cr2O7 2 minus is 10 to the power of negative 3. So number of mole dia 1. So tak adalah. Times the concentration of H plus. Okay, what is the concentration of H plus? And it is to the power of 14. Ada 14 mol H plus, so to the power of 14. What is the concentration of H plus? That's why at the beginning I said we need to focus on the pH. So we know that pH is equal to negative log concentration of H plus. Betul? Okay. So this pH is 2 equal to negative log H plus. So H plus concentration negative log bawa ke sebelah jadi berapa? 10 to the power of negative 2. Nah, ini matematik lah, you kena ingat balik. Dulu kita pernah belajar dalam AdMath ke MathMod, saya tak ingat lah. Ke matematik biasa. Jadi kalau kita bawa ke sebelah jadi berapa, bawa ke sebelah jadi berapa. Okay. So the concentration of H plus here is we get from the pH 10 to the power of negative 2. So dekat luar bracket to the power of 14 because we have 14 H plus. Okay, now you can get the potential E cell. Okay, after calculation you should get 1.06 volt. Kena try buat sendiri. Jangan tengok yang saya tunjuk je. You kena tulis supaya you ingat. Kalau you tekan calculator saja, nanti bila exam kita minta you tunjuk jalan kerja, you tak ingat. Okay, please do it on your own. And then make sure you get 1.06 volt. Kalau dapat lain, bagi tahu saya. Okay? Alright, so for exercise 3, what is the cell potential for the following reaction at room temperature? Is the reaction spontaneous under these conditions? Okay, so there are two questions, too many questions here. Right, so cell potential, look at the reaction given, you are given the concentration. So we are going to find the E cell. Okay, and then the question also asks you whether the reaction is spontaneous or not. Okay, so this one we are going to look at the final answer, right? And we are going to conclude whether it is spontaneous or not. Okay, so you are given this redox reaction, okay, and then you also given the half equation, half standard reduction potential equation. Okay, so both of them are reduction. So you need to determine which one undergoes reduction and which one undergoes oxidation. Okay, so look at the reaction given. The aluminium in solid form turns into aluminium 3 plus ion. Okay, so means that from 0, the positivity increase, means that it lost electron. Okay, now since it is 3 plus, so this aluminium lost 3 electron. Okay, and then for copper, from copper 2 plus ion, it become copper solid. From 2 plus become 0, means that the positivity decrease. Okay, decrease means that it gain 2 electron. Okay, 2 plus here becomes 0, means that it gain 2 electron. Okay, gaining electron, since electron is negative, okay, we minus 2 here, that's why we get 0 for copper solid. Okay, this one, which one is a reduction and which one is oxidation? Look at whether it gains or lose electron. Okay, so copper gain electron, it undergoes reduction. Aluminium lose electron, it undergoes oxidation. Okay, so since we are given the standard reduction potential, so for copper 2 plus reduced to copper solid, it is reduction, so we can straight away use this value. But for aluminium, it undergoes oxidation, the given one is reduction, so we change the direction of this equation. Okay, change the direction of the reaction. For oxidation, it will be aluminium solid turns into aluminium 3 plus ion equals, okay, plus 3 electron. And the E naught cell here, it will be negative E naught equals to negative 1.66 volt. Okay, so this one you are going to insert into this E naught cell. Okay, standard cell potential. Okay, equals to, remember the equation E naught reduction plus negative E naught oxidation. Okay, so for reduction, we straight away take the value, and then for this one, since we already changed here, so we can straight away use the 1.66. Okay, so for E naught cell, we will get 2 volt. Okay, so kat sini sebenarnya E cell. Okay, the cell potential E cell. Standard cell potential ada note kat atas ni. Okay, so this one the question asks you to find cell potential, not the standard cell potential. Okay, so E naught cell, we get 2 volt. And then How to find the E cell? By using the E cell equation. E cell equal to E node cell, okay, minus 0.0592 over N log Q, product over reactant, okay, equals to 2 volt minus 0.0592 over how many number of electron that we have. Okay, so this N refers to the balance equation. Okay, balance equation. Remember, to balance this equation, you need to make sure their number of electron are the same. Okay, so here the balance equation will be Al solid. Okay. So since this one has 3 electron, you must times 2, and this one has 2 electron times 3. Okay, so we will get 2 Al solid plus 6 electron. Okay, but then we will have another 6 electron for copper, for sorry, for reduction. So we already cancel out the 6 electron. Okay. Yang ni kalau tak nampak, you kena buat sendiri. Sepatutnya darab 3 kat sebelah sini. Darab 2 kat sini. Yang ni reduction kan. So dekat oxidation ni darab 2. Kalau kat sini saya takut you tertukar. Kita ambil reaction yang oxidation lah. Okay, 2Al2 and then plus 3 copper 2 plus. Okay, you will get 2Al3 plus. Okay, yang ni equals plus 3 copper solid. Okay, so this is the balance equation. Okay, so from the balance equation, we know that each of the reduction and oxidation reaction will have 6 electron. Okay, so yang ni saya dah cancel out lah yang 6 electron tu. Kalau you buat satu-satu. Sebab tak muat kan, so saya tak tunjuk satu-satu lah. Okay. So the number of N here is 6. Log Q. Okay, Q product over reactant. So what are the product? Okay, remember we are going to take ion only. Okay, this is the product. And for reactant will be copper 2 plus. Those in ion form. Okay, so we have aluminium 3 plus, which is 0.1 molar. Okay, since the balance equation we have 2 mole of aluminium 3 plus, then it is to the power of 2. Divide by the concentration of reactant, which is copper 2 plus. Okay, take the concentration given, 0.025 to the power of, look at the number of mole for balance equation, it is 3, so to the power of 3. Okay, so calculate the E cell. You should get, saya pun kena kira juga, jawapan tu salah. Okay, so this one, Okay. So the answer will be equal to 1.97. So this 1.97 is in positive. It is positive, right? So usually we don't write down the positive. But for redox reaction, we will put positive here to say that this reaction is spontaneous. Positive value means spontaneous. Negative value of E cell means non-spontaneous reaction. Okay, so to show the spontaneity, we will put the signage in front. So this one, 1.97 is positive, so it is spontaneous. Okay, so that is for exercise 3. So since we are doing titration, of course we have titration curve. Now we are looking at the redox titration curve. Okay, so what's the difference is that your titration curve will be still on the x-axis is volume, but now on the y-axis, okay, you will have the value of E, the potential, okay, the cell potential. Instead of pH for acid-base titration, PM for complexometric titration, PCl for precipitation titration. For redox titration, we have the potential, cell potential on the y-axis. X-axis sama, still lagi volume. Okay. So this is the calculation involved for redox titration. Okay, still the same, but the one that is different is the potential, standard potential. The titration curve for titration of 50 ml of 0.1 molar iron 2 plus with 0.1 molar cesium 4 plus in a matrix of 1 molar HClO4. So this is the equation given. You need to determine which one is reduction, which one is oxidation. Okay. Step 1, you need to calculate the volume needed to reach the equivalent point. Okay, so the number of moles should be the same for both of the element. Okay, so you are given the volume and concentration of iron 2 plus, right? So you can get the number of mole. So look at the equation given. We know that 1 mole of iron 2 plus will react with 1 mole of cesium 4 plus. So the number of mole will be the same. Since the number of mole is the same, now we can calculate the volume because we have the concentration of cesium. Okay, so after calculate, you will get 50 ml. Okay, kita tengok soalan balik Dia dah bagi dah volume dengan concentration of iron 2 plus and it give you the concentration of cesium 4 plus. Apa yang hilang kat sini adalah volume of cesium 4 plus. So boleh guna M1V1, M2V2 pun boleh. Okay. And then we can calculate on the before endpoint. For example, you add 10 ml of the titrant. Okay, adding the 10 ml of titrant, remember, lepas tambah aja volume akan berubah. Okay, but what you need to do first, same with precipitation titration, complexometric titration. In redox titration, you need to calculate the number of mole. Okay, we have iron 2 plus. And then we add 10 ml of cesium 4 plus. So ambil dia punya concentration dekat dalam soalan tadi 0.1 molar. Okay, we now have 10 mil. We add 10 mil. So this is the number of mole. And we can see that we still have more iron, 2 plus. Means that we didn't reach the end point yet. We are still at the beginning. We still have iron 2 plus left. Okay, so leftover iron 2 plus, we can calculate by 5 times 10 to the power of negative 3 mole minus 1 times 10 to the power of negative 3 mole of cesium ion. So we get the leftover. So this leftover will be divided with the new volume. Okay, so you get the concentration of iron 2 plus leftover. Okay, so we can calculate for iron 2 plus leftover, and we can also calculate for the Fe3 plus. Because from the equation, we know that 1 mole of okay, since we use 1 to the power of negative 3 mole of cesium 4 plus, means that we are producing same number of mole of iron 3 plus. Okay, tengok dia punya equation kat sini. Bila you guna 1 mole of cesium 4 plus, means that you are producing 1 mole of iron 3 plus. Kalau you guna 2 mole of cesium 4 plus, maksudnya you producing 2 mole of iron 3 plus. Okay, calculate the concentration for iron 2 plus and also the product iron 3 plus. Okay, and then find the standard potential for the half reaction in the standard reduction potential list. You get this one. So now you can calculate the E cell. Okay, we have the E node cell here for the reaction of iron 2 plus and 3 plus. And then use the equation given. This is 0.0592 divided by number of mole of electron involved. Okay, here number of mole of electron is 1. So N equal to 1. Log the concentration of iron 2 plus product over iron 3 plus reactant. So you get the E cell. Okay. Why we choose only iron? Because when we are doing the titration, kalau you tengok kat sini, volume of iron 2 plus is given, means that it is in the conical flask. The one that we use in the burette yang kita belum bagi lagi. Bila dekat dalam soalan, kita tambah 10 mil of cesium, means that it is in the burette. So the one in the burette will be at the x-axis. Sebab volume dia je yang berubah. Kita tambah cesium. So volume cesium yang berubah. So it will be on the x-axis. So E cell on the y-axis will be for the iron lah. Iron 2 plus. We are determining the iron by using cesium. Okay, and then step 3, after we add 60 mil. Sebab tadi kita dah kira volume for endpoint. Bila number of mole dia sama kan. Sekarang ni kita tengok untuk excess. Okay, calculate the number of mole for cesium 4 plus. 6 times 10 to the power of negative 3 mole. Maksudnya cesium dah excess. Okay, when we have excess cesium, we will get the number of mole for cesium 3 plus. Okay, will be equal to the initial of Fe2 plus. Okay, and then the excess cesium 4 plus will be equal to 1 times 10 to the power of negative 3 mole. So this number of mole should be divided with the new volume. Okay. So now we are calculating for cesium 3 plus and 4 plus because they are in excess. Okay, dah dapat ni, divide dengan new volume. So we will find the standard reduction potential for cesium. Okay, because it is in excess. Now we can get the E cell. Okay, E cell for the titration in excess. Okay, from that, ni dekat equivalent point. Tadi kita kira volume kan? Sekarang kita kena kira cell potential. Okay. For FE3 plus FE2 plus half reaction, okay, masukkan. You akan dapat ni equation, this equation, and then for cesium, this one. So since the concentration are the same at the equivalent point, their concentration are the same. So now you can put them together, the product and the reactant. At the equivalent point, the concentration are the same, the number of mole are the same. So now we calculating for all of them at the equivalent point. Kalau at the beginning we have leftover iron, excess we have more cesium. So at equivalent point they are the same. We are going to put them together. Okay, so we will get the new E cell. Okay. So just now we are looking at 10 and 60 also at the equivalent point. Sorry, not this one. Not. Okay, it's already given. Okay, we look at when we add 10 mil of cesium 4 plus and then we add 60 mil. Okay, this one is at the equivalent point. We get the inert cell. For your lab, you are going to calculate everything, right? So untuk assessment biasanya kita akan tanya beberapa volume sahaja. Okay, when you get all of them here, the value of E cell, you can draw the titration curve. Okay, so as I said just now, the volume of cesium 4 plus in the burette will be added. So on x-axis, it is the volume for cesium 4 plus. So this E cell is depends. At the beginning, we have leftover iron 2 plus. At the equivalent point, they have equivalent number of mole, equivalent concentration. So we are going to put all of them together here to get the equivalent, the E cell at the equivalent point. And then after equivalent point, we will have excess cesium 4 plus. Okay, so we only calculate for this cesium 4 plus producing cesium 3 plus. Okay. So for detection of endpoint in redox titration, there are 3 types of indicators. Kalau dalam EDTA titration pun kita ada 3, betul? We have Kalmer guide, sulfon, fast sulfon black, ada satu lagi saya tak ingat lah. Okay, tapi you guys kena ingat. Untuk redox titration pun kita ada 3. We have 3 commonly used indicators. And the first one is self indicator, which is no indicator. Sebab dia sendiri dah ada warna. The analyte also, already have their own color. So no indicator used. It is self indicator. MnO4 minus. The color is intensely purple. When we do titration, it become Mn2 plus. It is nearly colorless. Okay, no indicator used. We call it as self indicator. Okay, the analyte itself turns the color, change the color. Sometimes we also use the external indicator. Okay, we put it will form a colored compound with a specific oxidized or reduced form of the titrant or the titrant. Okay, for example, starch. It form a dark blue complex with iodide ion. Sorry. Okay, and the last one, we can use the internal redox indicator. So this internal redox indicator, it doesn't participate in the redox titration, but whose oxidized and reduced form differ in color. Okay, so there are 3 indicators used for redox titration. So that's all for chapter 9 and chapter 10 for BSK, complexometric titration and redox titration. Okay, so I hope these videos will help you on the calculation, especially for both chapters. Okay. If you have any question, please do the exercises for both equation for both chapters on your own. Okay. Tengok kat mana yang you lemah, and then please let me know if you have any questions. And since we already finished our chapter 9 and 10, next week there will be no class, but you need to use the class period to finish your assignment. Okay, so thank you very much, and I'm really sorry for what happened today. Okay, so take your time to watch this video on chapter 9 and 10. Thank you very much.